Welcome to the lecture series on engineering mathematics. In this series, we talk about linear differential equations with constant quotients. We'll discuss what are the various types of differential equations exist and how do we solve them. To start with, we'll start with algebraic equations, which are very fundamental to understand the linear differential equations. Right from our 6th standard or 7th standard, we used to come across algebraic equations. An equation that involves a variable which varies over a domain can be taken as a algebraic equation. For the simplicity, we'll talk about only algebraic equations of a single variable here. So as an example, x squared minus 5x plus 6 is equal to 0 is a simple algebraic equation where x can vary over a domain. In this case, if we talk about real numbers, if x varies over real numbers, this represents a simple linear equation, algebraic equation. Then what do you mean by solving this algebraic equation is we'll try to find out the points where the equation or the function fx is equal to x squared minus 5x plus 6 crosses the x-axis. For this function fx is equal to x squared minus 5x plus 6, we can easily observe that at x is equal to 2, 3, the function crosses the x-axis. So by solving this equation means trying to find out the values where the function crosses the x-axis. Now let us consider two variables. Let x be an independent variable and y is a dependent variable depending on x. The functional relationship can be established between x and y, and let us say y is equal to f of x be the function. Then we know the derivative concept dy by dx, which denotes the rate of change of y with respect to x in the physical sense. And when it comes to the graphical sense, it indicates the value of the angle, tan of the value of the angle made by the tangent to the curve y is equal to f of x. And given y, dependent variable depending on x, we can have higher order derivatives also, dy by dx, d square y by dx square, second order derivative, third order derivative, and so on. Now, an equation involving derivatives of the dependent variable with respect to the independent variable can be called as a differential equation. Differential equations can be classified into several types. Based on type of the derivative also we can classify them. We talk about the ordinary derivative dy by dx when y depends only on a single variable. If y depends on more than one variable, then we can talk about the partial derivative of y with respect to any of the variables, and such a derivative is called a partial derivative, and equations involving such type of partial derivatives is called partial differential equation. That is one variety. And if the equation involves only ordinary derivatives, it is called ordinary differential equation. Based on the order of the differential equation also we can classify them. By the way, the order of the differential equation is the highest order of the derivative that exists in the equation is called, it gives you the order of the differential equation. So in this example you can observe that d square by dx square is the highest order derivative. So the equation is second order derivative, second order differential equation. Similarly, we can have third order, fourth order, and nth order differential equations. That is another classification. Now, based on linearity and non-linearity is another type. When it comes to the non-linear differential equation, an equation where the dependent variable or derivatives of the dependent variable, if they are multiplied among themselves at least one location, then it becomes a nonlinear equation. In this example, d square y by dx square is equal to square root of 1 plus dy by dx whole square. Dy by dx is multiplied with itself, so it is a nonlinear equation. If no such multiplications exist, then we can classify them as a linear equation. Of course, there is also another definition for linear equation. We can talk about that later. And homogeneous equation. When the differential equation is of the form dy by dx is equal to f of x comma y, and if I substitute lambda x comma lambda y in place of x and y, and if I can take lambda out, lambda power n into f of x comma, if I can take lambda out of the function, then it becomes homogeneous. If it is not possible, it becomes non-homogeneous functions, non-homogeneous differential equations. So like this, we can classify them into several types, but here in this lecture, we are going to focus only on differential equations, that are linear differential equations. Again, constants of the quotients of the derivatives or the dependent variable are constants. So we're going to talk about linear differential equations with the constant quotients, homogeneous and non-homogeneous also. Given a differential equation, a solution of differential equation means finding out a suitable function f of x, y is equal to f of x, so that when we substitute that in the given equation, it has to satisfy. For example, in this case, dv by dt is equal to 9.8 minus 0.196v is one differential equation, and what is a suitable function that when substituted, it satisfies. It can be observed that v of t is equal to 50 plus c times e into minus 0.196t is a solution for this. Here you can observe that c is a constant of variation. For different values of c, you can have different solutions. So there are infinitely many solutions here, and once you fix a boundary condition or an initial value, corresponding c can be obtained so that you can find a unique solution in that case. So for different values of c, graphs are indicated here. They are all solutions of the differential equations for different values of c. So we can find such solutions for a differential equation. Let us focus only on linear differential equations with constant quotients. So the most general form, the homogeneous type we are observing here, is nth order derivative dny by dx power n plus a1 times quotient is there. A1 is a constant. A power dn minus 1 by dx power n minus 1, so on, plus a n y is equal to 0 is the most general form of a linear differential equations with constant quotients, that to homogeneous form. To start with, here different notations are followed. Y dash denotes dy by dx, y double dash denotes d square by dx square. There is one form can be used, and capital D can also be used as an operator, derivative operator. D by dx denotes capital D, so capital D of y is d by dx of y. So different notations are used in this case. You can observe here three types of equations are written here. Y double dash plus 2y dash minus 3y is equal to 0 is a second order linear differential equation with constant quotients. Similarly, d square minus 7d plus 24 is an operator now. Operating on y is equal to 0 is also a linear differential equation with constant quotients. We are going to solve such kind of equations now. Now we focus on finding the solution of the linear differential equation with constant quotients, homogeneous equation. The simplest possible equation that we can consider here is dy by dx minus my is equal to 0. Then from our elementary solutions of differential equations, we can observe that dy by dx is equal to my can be resolved so that it becomes a variable separable form. Once we separate the variables, dy by y is equal to m dx, then we can integrate them on both sides, so that integral dy by y is equal to m times integral dx. Now if we integrate on both sides, log of y is equal to m times of x plus constant of integration is there c, so we can have log y is equal to mx plus c, or taking exponentiation on either side, y is equal to e power mx plus c is the most general solution. When c is equal to 0, y is equal to mx is the basic form of the solution for the simplest possible linear differential equation. Why this is useful is we are going to take advantage of this observation, and we can use this to solve the higher order differential equations. General form of the solution of an nth order linear differential equation with constant quotients. One major advantage of linear differential equations is if we know that two functions fx and gx are two solutions of the linear differential equation, any linear combination of the functions also becomes a solution of the given equation. So by taking advantage of this, we'll start with the simplest possible solution by assuming that y is equal to e power mx be the general form of the solution for the equation. Since in the previous case we observed that for the simplest form y is equal to e power mx is the solution. So if it has to be the solution, then it has to, if we substitute the derivatives of this in the equation, it has to satisfy. Finding out the derivatives, dy by dx is m e power mx, second order derivative is m square e power mx, third order derivative is m cube e power mx, so on, nth order derivative is m power n e power mx. Now if we substitute all these things in the given differential equation, we can take e power mx as common, and m power n plus a1 m power n minus 1 so on an into e power mx is equal to 0 is the equation reduces to this. Now it can be observed as a product of two terms. One is m power n plus a1 m power n minus 1 so on an. The other term is e power mx. By the properties of exponentiation function, e power mx can never be 0. So the product of the terms is 0 and e power mx can never be 0. The only possibility is m power n plus a1 m power n minus 1 so on an is equal to 0 is the only possibility. But this is an algebraic equation involving a variable m and the order is n. Now we know how to solve a algebraic equation, right? So if we solve this equation, there will be n number of roots for the equation. Let us assume that m1, m2, so on mn are the roots of the equation. Then, because of our assumption y is equal to e power mx is a solution, for each of these roots, we'll have n number of solutions. So, y is equal to e power m1x is one solution, y is equal to e power m2x is one solution, so on, y is equal to e power mnx is also a solution because of our assumption. Now, because of the linearity property, the most general solution can be constructed as a linear combination of these independent solutions. Y is equal to c1 e power m1x plus c2 e power m2x on cn e power mnx is the most general form of the solution of the given differential equation. This is a theoretical approach. For any given differential equation, we can use this method and to find out, reduce it to the algebraic form and find the roots, and from that we can construct the general solution.